final solution defined by the contour C1, which is between our branch cards. Right, so as you remember, the saddle of our exponent function is positioned at point t is equal to minus x. And so it's either to the left of the branch card, of the left-hand branch card, or to the right of the right branch card. Here or here, depending on the fact that x is positive or negative. So for this reason, it's unreachable for this contour, right? Because if we want this contour to pass through the saddle at large positive x, again, we encounter the same problem. So it should go here. So the steepest descent direction and the allowed regions are here. So if we draw the contour through this saddle, then we need to return to this middle region, and so when we are going to when we are returning, we pass through this forbidden region here, right? So now we've come to the conclusion that the saddle doesn't contribute to the asymptotic of the function defined by this C1 contour. So then, how would we compute the asymptotics? So suppose, let's try to do this if x is large and positive. So, right. So what would, again, so if the saddle is unreachable, then the only possible points which could contribute to our asymptotic behavior are the branch points of our integrand. So, for example, if x is positive, then the steepest descent direction from this branch point is the negative axis. Well, actually, it's identical here and here. This is the steepest descent direction. So the idea would be, for example, to shift the contour to the right or to the left. So let's actually try to shift this contour to the left and see what's going to happen with our deformation, so how it is deformed. So if we are shifting it to the left, so we are moving left and left and left till it touches this branch point. And the deformation would be something like this, actually. So it should come to this point from the steepest descent direction, circle around it, then slip on another Riemann sheet below this surface, and go into this upward direction. So that would be the correct deformation, which defines the behavior of our solution and at large and positive x. So you may ask why this deformation is not good. Well, let's try actually to figure out what's going to happen if we shift the contour to the right instead. So okay, let's do this. So what is happening? So we shift it here, and we actually can come to this point, t is equal to 1, into the steepest descent direction. Well, in this case, it's ascent, but anyway. So it seems perfect, so it's good. But then the question is, how do we return to continue into this upward direction? Well, so now we investigate our final solution defined by the C1 contour. So as you remember, our exponent function, this, has the saddle at point t is equal to negative x. So for large x, this point lies to the left, either to the left of our left branch card when x is positive, or to the right of our right branch card when x is negative. In either case, the saddle is unreachable for our contour. Why? Because as you remember, we have this steepest descent direction, which is vertical, and these allowed regions along which the contour can approach the saddle. So, and we encountered the same kind of problem we encountered before. So if we, for example, shift the contour so it passes through the left saddle when x is positive, then so we can shift it so it passes, it can approach this from this down direction. But then when it moves up, it should return to our initial region, which is between our branch cards. But when it returns, it will pass through this forbidden region, which lies above our saddle point, so which is bad. So we can't do this. So in the same situation is takes place when our x is negative and we try to reach the right-hand side saddle, right? So the same situation. So these, in both cases, the saddle is unreachable for this central contour. So our only choice, the only choice of singularities or special points are the branch points. So now we come to the conclusion that it is the branch points which define the asymptotic behavior of our solution, right? So for example, let's assume that x is large and positive. Then the steepest descent direction from the both branch points is this left real direction. Here it is. It's here and it's here, right? So now the question is, how do we actually need to deform the contour so it facilitates the finding of our asymptotic behavior? So let's try first to shift the contour, for example, to the right. So if we do this, well, actually, we can deform it in such a way that it can approach this branch point in the steepest descent direction. And then so it can enter this branch point, but then it should go out of it in some direction, well, obviously in the upward direction. And those are the parts of the contour which contribute the most significant part into our asymptotics. And as you see, they are passed in opposite directions. So this contribution basically cancels. So if we shift the contour to the right, we can't find any reasonable asymptotic. So we just get zero, no contribution at all. So let's instead try to shift our contour to the left. So suppose we are moving slightly to the left of our branch card. So what's going to happen? Let's see. So if we do this, then our contour going from this down region, then since it should pass into this central region, it should approach the saddle from this steepest ascent direction. Then you can circle around it, but then ideally it should go out from this from this branch point again in the steepest descent direction, but it can't do it because there is a branch point here. So what we do again, so we should slip onto the Riemann surface, Riemann shift, which lies beneath the first one, and go into this upward direction, but on this lower Riemann sheet. Okay. Now, okay, let me actually show you this deformation. So, right. So this is the illustration. So this is the initial position of our contour, and this is how we deform. And you see it slips below to this Riemann sheet, lower Riemann sheet. Okay, here we go. Now, now let's actually compute this asymptotics. Right. So x is positive. Again, we do the same kind of thing. So we expand our exponent of our exponential function in the vicinity of this t is equal to -1 point. So t, as before, t is equal to -1 plus s. Then the exponential function is simplified. It becomes e to minus x plus sx. dt is equal to ds divided by the square root of 2s. And now we need to choose the correct value for our multivalued function g of t. Again, so here it's positive. And right, so when we go here, both complex numbers, t minus 1 and t plus 1, has to make this pi rotation in the counterclockwise direction. So the full change of the argument of t squared minus 1 is minus 2 pi. Square root is going to give us minus pi. And so here we go. Right. and we approach this function, so this point from large s to small s, so the integral is taken from plus infinity to 0. And then we make a full rotation, and then go along this steepest descent direction from this point, so the integral is taken from 0 to plus infinity over ds. And okay, so we have the same kind of expansion, minus x plus sx, right, ds over square root of 2s. And so t minus 1, t plus 1, make this clockwise, full clockwise rotation plus 2 pi. So, right, so when we go here, okay, let me, so here, this function makes pi rotation, and this function minus pi rotation, and this function makes pi rotation in this direction, so the full change of the argument is 0. So when we are on this lower Riemann sheet of our g function, then the argument, so the value of this g function is positive, right? So no sign at all. Right, so now we have this simple combination of our two integrals. E to minus pi is -1, so we just sum them up to get 2 times integral from 0 to plus infinity. E to minus x can be factored out. And we introduce the change of variables, say, okay, okay, so sx is equal to actually v, and right, and then we have. Так, мне нужна пауза. Сейчас я подумаю чуть-чуть. Сейчас. Минус 1 плюс f. Сейчас. Можно пока выключить камеру. Сейчас я соображу. And here, by the way, we have to keep in mind that this s variable is, in fact, has its modulus and its argument. So s, as you see, it's a complex number, so we can represent it as s is equal to modulus of s, which is, I don't know, rho, for example, times e to I pi, right? So we almost lost this sign. So now we have this minus rho x. So this is going to give us d rho to e to I pi. Так, нахер, короче, все. Да. Значит, тут была допущена небольшая, значит, погрешность. Значит, с момента появления надписи t равняется минус 1 плюс s, вот этой замены, нужно осуществить перезапись. Вот, потому что дальше будет слегка отличаться изложение от того, что было написано раньше. То есть вот она появилась, и дальше мы останавливаем и делаем следующую запись. Все. Right, so after this change, well, when we do this change, we have to keep in mind that s parameter here, it's this complex. So we integrate along this direction, along this path, which approaches this branch point. And s, in fact, is a complex number which faces into this, points into this leftward direction. So s is equal to modulus s to e to I pi, for example, right? So let's actually represent it as some argument or some modulus and the argument, right? So now what we do, we expand our exponent function in the vicinity of this minus -1 point, right? So the expansion is, of course, very simple. So it's e to minus x plus sx, but s is now minus rho, so minus rho x. The integrand is taking along this rho, and rho changes, the distance changes from plus infinity to 0. So dt is equal to ds, obviously, but ds is equal to minus d rho. So it's minus d rho. And divided by the g of t function expanded near this -1 point. We already did this, so we know the answer. The modulus is going to be the square root of 2 rho. But now we need to find the argument of the sign of this square root, right? So here our g function is positive, right? And so when we move into this region, this t minus 1 makes full 1 minus pi rotation, and t plus 1 makes another minus pi rotation. So the full rotation is minus 2 pi. Here the square root gives us minus pi, and here we go. Right. Then the next integral, as you remember, so we slip onto this lower Riemann sheet, and the only difference between this branch, this part of the contour and this, is that t plus 1 complex number makes the full rotation in a clockwise direction. Right, so the expansion of the exponent looks the same. The integral is taken from 0 to plus infinity. Again, d rho over square root of 2 rho. And actually, d rho, as you remember, with negative sign, so it's minus d rho. And the change of the argument. So, okay, let's just to make sure. So here our g is positive. To get here, this complex number makes pi rotation in the counterclockwise direction, but this complex number makes the rotation in the clockwise direction. So this gives us minus pi change, and this gives us pi change. So minus pi plus pi is 0. So there is no, so on this lower Riemann sheet, this g function is again positive as well as here. Right, so no sign at all. And now we sum up these two integrals. So here is minus sign gives us plus, and we interchange the limits of integration to get another minus. So and here, so we have two minuses here, so they sum up, so they don't cancel each other. And this remaining integral is a gamma function, right? So it's -2 times gamma function of 1/2 divided by the square root of 2 and by the square root of x, actually. And the gamma function of 1/2 is square root of pi. And what we get in the end is, okay, it's minus square root of 2 pi divided by x. And sorry, I dropped this exponential decaying factor. So this is the asymptotic of our solution, defined by contour C1 and large and positive x. The question is, what's going to happen if our x is large and negative? So let's discuss this case. So this situation mirrors the previous one. So what's happening is that the steepest descent direction is changed. Останавливаем. So here I raised the previous deformation of the contour. So now x is negative. So the steepest descent direction from the branch points is now the positive t direction, like that. So how do we shift the contour now? Well, we make a guess, educated guess. So since for large and positive x we shifted it to the left, well, our guess is that we need to shift it to the right. So let's check. Indeed, if we do this, if we shift it to the right, then our contour maybe shift it like this. And then it approaches now the right branch point in this steepest ascent direction, circles it around, and then it goes out of it in this steepest descent direction, right? So if you want sometimes to avoid this slipping to this lower Riemann sheet, what you can do instead, let me show you. You can actually bend the branch cut itself. So you can, and this will never lead you to a mistake. And now you may restrict your attention to a single Riemann sheet. Right? The two approaches are just completely identical. Well, this one certainly looks more exotic, but still it's a correct one. Okay, so let's figure out what the asymptotics of our solution for this situation is. So first we approach this branch point from this positive direction, right? So our g function is in this direction, in this region, it's positive. So the expansion of our integrand looks very simple. So it's just the integral from, so we expand, so we shift, we make the change of variables, t is equal to 1 plus s. And now our s variable is just standard positive complex number, or positive real number actually. So s changes from plus infinity to 0, e to so e to x plus sx, okay, dt is equal to ds over square root of 2s. Yeah, I think that's it. So this is it for this lower branch integral, lower band integral. Now the second one. This one goes from 0 to plus infinity, e to, again, x plus sx, ds over square root of 2s. Right, and as far as I understand, the sign should be changed. Let's see. Indeed, so when we go along this direction, this complex number, I mean t minus 1, makes the full rotation in the counterclockwise, in the clockwise direction. So the change of the argument of, well, this one, t plus 1, doesn't change sign, doesn't change argument at all. So the full change of the argument of t squared minus 1 is minus 2 pi. So then, since its square root is minus pi, so it should be e to I pi. Right? So we have this negative sign here. We interchange the limit and earn one more minus in the first expression. And when we sum them up, we again have a gamma function type expression. So it's minus 2, the integral e to sx from 0 to plus infinity, ds over the square root of 2s and e to x. Right, and the integral is convergent because, as you remember, x is negative, so it's fine. So it's a simple, again, gamma function. And the answer is just identical to the previous one, up to the change of the modulus of x to the modulus of x. So here is the answer, square root of 2 pi. Sorry, here I dropped square root sign, over the square root of the modulus of x times e to x. Right. So this is the asymptotics for our function at large and negative x. And you see that we are in luck because we have a convergent expression for positive x and the convergent expression for big and negative x, right? So we actually can unite these two asymptotic behavior into a single one, like y of x. Oh, by the way, we didn't fix this integration constant a. So it's a minus a over times the square root of 2 pi over the modulus of x times e to the modulus of x. Right, so this is our correct asymptotic minus. Correct asymptotic behavior for big, large, and positive and negative x. Now, the last thing is left is to fix this integration constant a. As you remember, we fix it by the condition at the origin. So the solution at the origin should be, again, bounded and equal to 1. So, right, let's do this quickly. Так, все. И последний, я думаю, 5. And finally, the last step. So, let's actually write down our exact integral, how it looks like at the origin. So x is equal to 0, and the integral is simplified into the following expression. So to compute this integration constant, well, we sometimes need to just shift the contour or to deform it in such a way that it facilitates the computation of, so it assumes the simplest form for computation. In our particular case, so our initial position of the contour is some arbitrary line or curve belonging to this middle region between these branch cuts. But it's quite obvious, so if we, for example, move the contour so it coincides with the imaginary part in the t-plane, or of the imaginary axis in the t-plane, then, well, the integral probably is going to be simplified as well. So let's see what's going to happen. So now t is equal to is, and s stretches from minus infinity to plus infinity. The only possible thing that we need to do is to extract the correct value of this square root of t squared minus 1. So again, here is our g function. The g function is positive. And then when we move here, only t minus 1 complex number makes rotation minus pi. So the argument of the full expression is going to be e to minus I pi by 2. And since it's denominator, it's going to be e to I pi by 2. So our integral now is equal to a times the integral from minus infinity to plus infinity. dt is equal to I ds divided by s squared plus 1 e to minus s squared over 2, and then another I, so coming from this minus pi rotation. And here it is. So it's minus a times this integral. Well, this is just some number. Actually, it's almost 2. It's equal to approximately 1.98, but it can be expressed via a special function. It is expressed via Macdonald, so-called zero-order Macdonald special function. You can look up its integral representation, and if you do it, you will get the following result. So, and Here it is. So here is our normalization constant. We computed it. So now it's equal to e to 1/4 divided by this 0-order Magdalene function and this minus sign. So finally, we have our full solution of this differential equation. We found the solution in terms of exact solution in terms of this contour integral. We fixed the position of the contour, so it should belong to this region between the two branch cards. We fixed their normalization constant, and we also found the asymptotic behavior of the solution at large and positive x, large positive and negative x. So this is the maximum we could hope for such a, in principle, difficult problem. We know almost everything. Right, so that's it for today, I think. Thank you for your attention.